Hi students, in my last video I have started the refrigeration cycle and the definition of refrigeration and the difference between heat engine, heat pump and refrigeration, and we have seen what is a COP, the formula for COP, and the classification of refrigeration cycle. There are four refrigeration cycles: air refrigeration, vapor compression, vapor absorption, steam jet refrigeration. Again, air refrigeration cycle is classified into two types. One is reversed Carnot cycle, next one is Bell-Coleman cycle. So now let us see what exactly the air refrigeration cycle is all about. So if you look at the air refrigeration cycle, the name itself says air is used as a refrigerant. That's why it is called as air refrigeration. Now I have written here refrigerant is used as air, and let's see now what are the basic components that we come across in air refrigeration cycle. So like all other refrigeration cycle, this refrigeration cycle is also having components like compressor, evaporator, condenser and turbine. So these four components will be available. So let me draw the schematic diagram. So I'll put condenser here and compressor, and evaporator is here, and turbine. So this is the turbine. So I'll start from here. So air refrigerant, the refrigerant enters into the compressor. This is the first state and goes to the second state, and it enters the condenser from second state to third state, and from third state it enters turbine. Work is developed, and from here to fourth state. So this is the refrigerating cycle. So first to second air is compressed, and second to third air is condensed, and 3 to 4 turbine work, and work output will take place, and again after 4 it will enter into the evaporator, and here the refrigeration process will take place. The space is cooled and will go back to this compressor once again. So this will be circulating one again and again in the same refrigeration cycle. So same thing has to be drawn in PV and TS diagram. So for every cycle, in the previous chapters or topics, we have discussed all the components or after all the refrigeration cycles. Those things will be shown in the graphical representation. So this is pressure, and this is volume, and this is temperature, and this is entropy. So this is pressure, volume, temperature, entropy. First we will start this 1 to 2 process, which is compression. So air is compressed adiabatically or isentropic. Entropy remains constant. So entropy remains constant, compression takes place. So in PV diagram 1 to 2 process like this, and 2 to 3 process isothermal. So temperature is equal to constant. So air will be expanded, otherwise compression takes place. 2 to 3 process, in what way? Isothermal compression. So 2 to 3 process is the isothermal. This is adiabatic, PV to the power of gamma is equal to constant. This is temperature is equal to constant. Now 3 to 4 turbine work. So turbine, what happens in the turbine? Expansion takes place. So expansion means what? So pressure decreases and volume increases. So 3 to 4 process is the expansion process. What kind of expansion? Isentropic expansion, PV to the power of gamma is equal to constant. Again 4 to 1 process is what? Isothermal process. Isothermal expansion. So isothermal expansion will be shown in the PV diagram as like this. If you look at the PV diagram, so this one and this one will be adiabatic process. This is adiabatic or isentropic compression. This is isentropic expansion. And 4 to 1 and 2 to 3 is temperature is equal to constant. Isothermal compression, isothermal expansion. So this is the PV diagram of this air refrigeration. The same thing has to be shown in the TS diagram. So 1 to 2 process isentropy, that means entropy is constant. So I'll draw like this. So this is 1, this is 2, this entropy remains constant. If you look at this 2 to 3, temperature is constant, but what kind of temperature is constant? Isothermal compression. Compression means what happens? Entropy decreases and temperature remains constant. So 2 to 3 process isothermal. So T2 is equal to T3. And next 3 to 4 process is adiabatic, otherwise isentropic. Isentropic means what? Entropy remains constant throughout 3 to 4 process. And last one is isothermal process, temperature is constant. So the cycle goes like this: 1 to 2, 2 to 3, 3 to 4 and 4 to 1. So in this process, work done, this is compressor work done. 3 to 4 is turbine work done of turbine, and 2 to 3 process is heat addition, heat rejection. 1 to 4 process is evaporator, so heat is added, so QA. So heat is added QA and heat is rejected here. So this is the PV and TS diagram of air refrigeration cycle. So now look at the derivation part. So now we'll see how that air refrigeration is derived. So from TS diagram, first let us take the TS diagram. For our derivation part, we'll take this diagram into consideration. So first one is heat absorbed. So heat absorbed is equal to QA. Heat absorbed, heat is Q and A is absorbed. Heat absorbed is equal to, where heat absorption takes place during 4 to 1 process. This is 4 to 1 process, heat is absorbed by the refrigerant. So heat is absorbed. So QA is equal to, how can we write? So temperature, T1 temperature, T1 into S4 minus S1 minus S4. So S1 will be greater, S4 is smaller. So this difference will be S1 minus S4. So this is the heat absorbed formula. The same way, what is the heat rejected? Heat rejected, how can we write? QR. So where heat is rejected? 2 to 3 process. What is 2 to 3 process? Condenser. In condenser, heat is rejected. In the same way, we have to write what kind of temperature is there, T2 or T3. So we'll write T2 into, which is the highest entropy, S2. So S2 minus S3. So this is the heat rejection process. This is the heat absorption process. So now we have found out both heat absorption and heat rejected. So first we will see from first law of thermodynamics. You might have studied first law of thermodynamics. So what we have studied in the first law of thermodynamics, heat supplied plus work done is equal to heat rejected. So this can be again written as work done is equal to how the work is done. So there are a difference between heat rejected minus heat absorbed is nothing but work done. So work done is equal to heat rejected minus heat absorbed. So the same thing we have to substitute in this equation. In the place of heat rejected, I am going to substitute T2 into S2 minus S3 minus heat absorbed T1 into S1 minus S4. So work done, we have found out the equation. Now COP we will write. COP is equal to refrigerating effect divided by work input. So this can be represented as QA divided by W. So how can we write QA? T1 into S1 minus S4. So how can we write work done? This entire equation we have to write. So T2 into S2 minus S3 minus T1 into S1 minus S4. So what we can do is, so if you take T1 in the numerator, T1 S1 minus S4 divided by, if you take T2 minus T1 separately, so we will get S2 minus S3. So one more thing is temperature T1, T2 minus T1, S3 minus S2 is equal to S1, S3 is equal to S4. So in the place of S4 we can write S3, in the place of S1 we can write S4. So if you rearrange, so what we are going to get? So the same equation will be T1 into S1 minus S4 divided by, if you take T temperatures separately, so you are going to get S1 minus S4. So both things are cancelled. So finally you are going to get COP as T1 by T2 minus T1. So this is the COP of the air refrigeration cycle. So we have seen the derivation. So first the thing is the components, and then the working principle, and then PV diagram, and then TS diagram, and we have seen heat absorbed formula, and we have seen heat rejection formula. The same thing we have substituted in first law of thermodynamics, and COP we have written the formula, and we have substituted all the values, and finally we have reached the COP in terms of temperature, which is nothing but T1 by T2 minus T1. So this is the COP of air refrigeration cycle. Thank you.